All right, let's go ahead and take a look at a couple more examples here. And the first example tells us to evaluate the derivative of the function at the given point, and then use the graphing utility, so use your calculator to verify. I prefer just to assume that I'm correct, and that's just an egotistical way of looking at it, but I found out that the bigger the ego, chances are the better you do in math. That's not exactly true, but seriously though, you have to have some confidence in what you're doing, and you'll find the more confidence you have, the more successful you'll tend to be. Okay, so as we start here, let's go ahead and find the derivative. Now, to do that, we need to find out what the top and the bottom functions are, because we need to invoke our quotient rule. And so I'm going to identify the top as f, 1 plus cosecant x. F prime then is equal to, now the derivative of 1 at 0. The derivative of cosecant, as we found out, was negative cosecant x cotangent x. G is the bottom, which is 1 minus cosecant x. And G prime then is just the negative of that. And so it's cosecant, the other cosecant, the kind with an S. Cosecant x cotangent x. Okay. So now that we have that, we can go ahead and invoke our quotient rule. So we have y prime is equal to the derivative of the top, which is negative cosecant x cotangent x, minus the derivative of the top times the bottom, which is 1 minus cosecant x, minus the derivative of the bottom, which is cosecant x cotangent x, times the top, which is 1 plus cosecant x, all over the bottom squared. 1 minus cosecant x quantity squared. All right, so let's go ahead and see if we can't clean this up just a little bit. So we've got a negative cosecant cotangent times 1 for negative cosecant cotangent. And then we've got a positive cosecant squared cotangent. I think I'm going to run out of room here. So I apologize, I'm going to have to continue this down on the next level. Minus, and we have a cosecant x cotangent x, negative, and so that's going to be a negative cosecant squared x cotangent x. Okay, that finishes it out 1, 2, 3, 4 terms for the top. And then we have the 1 minus the cosecant x quantity squared on the bottom. Notice that I have a positive cosecant squared cotangent and a negative cosecant squared cotangent. Those cancel out, and I'm left with y prime then is equal to negative cosecant. Oh, I have 2 of them, so that's negative 2. Negative 2 cosecant x cotangent x divided by 1 minus cosecant x quantity squared. Okay, now it looks like I might be able to use some kind of a trig identity. I can't think of it right now, but it's unimportant because all we have to do is evaluate it at at x is equal to pi over 6. Okay, so now to evaluate it, we actually draw a vertical line and say evaluate that at x equals pi over 6. And when we do, then I always remember this as pi over 6 is equal to 30 degrees. This is my science my science upbringing talking here. Pi over 6 is 30 degrees. Sine of 30 is a half. Cosine of 30 is root 3 over 2. So we really have negative 2 times 1 over sine of x, or 30 degrees, is 1 over 1/2, which is 2, times cotangent. Cotangent is in fact cosine, but cosine of 30 is root 3 over 2. Cosine of, or sine of 30 is 1/2, all over cosecant. This is 1 minus, and now cosecant, remember, is 1 over half, or 1 over sine, which is 1 over half, which is just 2 squared. All right, now in this case, what is on the bottom comes to the top, and so that cancels with that, and I'm left with -4 root 3. Negative, or 1 minus 2 is -1. That quantity is squared, which is 1, and so there's my answer. So my derivative was -2 cosecant x cotangent x all over the quantity 1 minus cosecant x squared. And that was evaluated at pi over 6 to give me -4 root 3. And that's what the question was asking us. Another question that's, well, somewhat similar to it, but we don't have to deal with any trig functions. Find equations of the tangent lines of, to the graph of f of x is x plus 1 over x minus 1 that are parallel to the line 2y plus x equals 6, then graph the function of the tangent lines. Okay. Well, we want to find them that are parallel, which means the slopes have to be the same. The slope of the function is its derivative, and so we must find the derivative of that. But first, we have to identify what our functions are. So I'm going to let h of x be the top, which is x plus 1. Its derivative then will be 1. G is going to be the bottom, which is x minus 1. Its derivative is also 1. And so the derivative of f, then in that case, is the derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. Okay? So f prime of x then is equal to, this is x minus 1 minus x minus 1 all over x minus 1 quantity squared. If you'll notice, x and negative x cancel, so I'm left with -2 over the quantity x minus 1 squared. Now, that means the slope of that function obeys this rule. So now the question is, find equations of the tangent lines to the graph of that are parallel. So we need to know the slope in order to find out if it's parallel. So we have 2y plus x equals 6, and that implies that y is equal to -1/2 x plus 6. -1/2 is our slope. Okay, so putting those two things together, my derivative must be my slope. And so that means that -2 over x, the quantity x minus 1 squared, must be or must equal -1/2. If you multiply both sides by -2, you cancel the fraction on the right. So you'll have 4 over the quantity x minus 1 squared equals 1. Solving for x from there, you'll multiply both sides by the quantity x minus 1 squared to get 4 is equal to x minus 1 quantity squared, which means that plus or minus 2 is equal to x minus 1, which means that x is equal to 1 plus or minus 2. So x is either -1 or 3. Now be very careful here. We need equations for the lines because we have to find the lines parallel. So that means that we need a point, we need a slope. We know the slope, we have the x values, now we need the y values. Okay, now the first time I did this, I did something silly and I plugged my x values back into this line here. But that's not what I need to do because that is the line that they're parallel to. I have to plug it back into f. So now that I have that, what is f of -1? Well, that's -1 plus 1 over -1 minus 1, which is 0 over -2, which is 0. So the point -1, 0 is where they touch. as well as f of 3 is 3 plus 1 over 3 minus 1, which is 4 over 2, which is 2. And so that's 3 comma 2. Okay, so these are the points. Points of intersection. Okay, so now, y1. The first one I'm going to do from -1. So I have, I want to, because I'm using a point slope formula, so I don't want to confuse myself. Y minus 0 is equal to -1/2 the slope times the x plus 1. It's x minus a -1 in point slope form. Okay, so that means that y is equal to -1/2 x plus 1. Notice I'm not changing the look of it. My other one, though, is y minus 2 is equal to -1/2 x minus 3. Again, I'm not changing the look of that. I don't mind that it looks like that because I can graph that. And of course, we were told to then graph the function and the tangent lines. This is the first part. We were told to find the equations of the lines that were tangent to this function and parallel to that line. That's 1. This is 2. Okay? So now, I've already graphed out the original function. And you can do this on your calculator and then transpose it onto your graph. That's fine. But the way that I did this is I knew bad things happened at +1 because of the denominator being 0. So that created that vertical asymptote. After that, I had forgotten how to find the horizontal asymptote. And so I simply started choosing values of x and then finding the y. So let's go ahead and put these functions in here. I'm going to do the first one. Y is equal to -1/2 times the quantity x plus 1 in yellow. And in green, I'm going to do y minus 2 is equal to -1/2 x minus 3. Okay, so let's do the green one first. So it has to pass through the point 3, 2. Okay, so 3, 2. So it's tangent right there. And it has a slope of -1/2, and so it's going to be kind of shallow. And so it's going to come down 1 and over 2. And so it's going to look kind of like this. Okay. Now, my other one here goes through the point 0, -1, 0, -1, 0. And so it hits right there and has the same slope. And this is going to look a little different because it's parallel to that line. But even though it looks like it crosses my graph twice or 3 times or 4 times, yeah, it's the hand drawing part. And so that's what it looks like. And so you have your two functions that that are tangent to the original. And those are the tangent lines at that slope.